Hey class, so this is going to replace any recording we would have made of that really difficult lecture when Electa was acting up badly. I think we got through the major content, so I don't think we'll be slowed down um, as far as our content in the course, but I think we will add an extra lecture on at the end, maybe a fun one if people can't make it, but we'll try to make up for that disaster, a different disaster than Week 8. But Week 8's disaster was very fruitful. I'm very, very glad that we kind of hit that thing. And I really encourage you guys, sorry, my dog and cat are fighting in the background. I really encourage you guys at any time you're having a wait a minute to let me know because I think this is really good stuff. So as I mentioned in the beginning of the other one, why all this wave stuff? And if you haven't had a chance to watch the recording that was assigned for reading, I think in week 7, go back. The link is there. It's working now. So Einstein's Big Idea. I got this license for our class through the PBS education thing. So do support your local PBS station. Be on the lookout for the man who made the wall around Paris. We've talked about him a bit. We'll talk about him more. Du Châtelet and Energy, and also be on the lookout for the trains. The light, riding a beam of light on, riding a train that's going the speed of light, and then different ideas that Einstein has about, well, what would that mean? Could I hold up a mirror? What would I see? So all sorts of these questions, and we are going to work with these, especially when you start building your Minkowski diagrams. Your Minkowski diagrams are going to help you navigate through space-time. So that's one of my goals for you guys. You will start that before the end of the semester. You'll start navigating in space-time. Another reason to put up with all this wave stuff and get good at it is the equation, E is equal to mc squared. And we had a great question, which was, what does E is equal to mc squared mean? And boy, that it means a lot of things. It doesn't mean exactly what everybody thinks it means about if you had some sort of machine to convert matter into energy, but it is a way of, and also we'll talk about how Einstein himself didn't understand all the things that it meant. It was more about his discovery of this relationship, and then all the implications that came out later were things that he was a little bit hesitant, sort of like Max Planck saying, whoa there, guys. But E is equal to mc squared is going to involve light in a very specific way that we are getting close to in what we're doing. And that is, we're going to follow along with minute physics and the story of this cat. And this cat is going to emit some light. Now they say radioactive cat. It is a radiating cat. The cat is radiating energy. That means energy is coming out in all directions. This cat has flashed a beam of light, and energy is coming out in all directions. When the cat does that, since energy is conserved, when the cat pushes energy out into the universe, the cat himself must lose some energy. How do we calculate how we calculate that is very interesting based on this minute physics setup of this, and it's just brilliant the way they've done this. So in one scenario, the cat is floating in space. We get in a rocket, and we start flying at a certain velocity. From our frame of reference, looking out the window, relative to us, the cat now has kinetic energy. The cat then flashes the light and loses this amount of energy. In another scenario, first the cat flashes the light, then we get in the rocket, and then at the end, the cat should have the same amount of energy both ways. This is the equal sign, and we're going to set up things on either side. Now, to get to how much energy the cat has lost, that's where we're headed with all this wave stuff. So immediately, our next lecture, in lecture 10, we're going to talk about the energy in waves. But for now, let's keep talking about waves, because we're going to come back to light so many times during this year that just understanding the waves is more than just being able to calculate E is equal to mc, or derive E is equal to mc squared. So let's talk again about our definitions. You guys did a great job on the call when I was just doing audio doing this. A wave is a disturbance that travels through a medium, and I put a little asterisk there because we're going to talk about light and a medium in the very next unit. a disturbance that travels through a medium from one location to another. The wavelength is the length of one complete wave cycle, the up and the down. So a pulse wave is not considered a complete wave cycle because it doesn't go all the way up and all the way down. The Muggle answer is it's a distance from peak to peak or trough to trough. That helps them understand, the Muggles, that a pulse wave doesn't count. So it is important, this peak to peak and trough to trough, to keep in your mind to remember that. But, for example, this point all the way over to this point would also be one complete wavelength. Frequency is the amount of time it takes for an entire wave to go through a single point in space. It's measured in wavelengths per second. So here's like, I'm watching this particular thing, I'm at the peak, per second is how many wavelengths can go through that each second. So I guess I should rephrase it a little bit, the definition of the frequency. I got it from a really good physics site though. Okay, amplitude is the distance from equilibrium for how high the wave is before the wave began, not from the trough. So the amplitude here, this is the maximum amplitude for the wave, so it's often called the amplitude of the wave. But at each individual point, the distance would be the amplitude. But the amplitude of the wave is measured from equilibrium, not plus and minus. This would be twice the equilibrium. So that's a big thing that people miss in their freshman physics year. So I just want to bring that home. When we're working in the wave on the string setup, remember we're mostly looking at oscillations. Light is an oscillation. Most of what we'll do, unless you are in electrical engineering and go on to something like 6001, 6002, you really won't work much with pulses. And usually we put no end. Fixed end if you want to see a reflection. And damping, we take the damping all the way down, except in the resonance homework you guys, and it looks like everybody did for week 8. In a transverse wave, the particles go up and down, and the energy moves across. So the particles are really, now they move a little bit. They move in this little circle. If you watch a beach ball on the ocean, you can watch it move in this little circle. But notice that it's really staying right there. This actually shows how the movement goes through the depth in ocean waves. If you're interested in this kind of stuff, oceanography, oh, there's so much. I took a class, in fact, that was, I took a class from a professor who took a class from Lorentz. We're going to talk about Lorentz later. So now that you've taken a class from me, you've taken a class from a person who took a class from a person who took a class from a person who took a class from Lorentz. I think I put an extra one in there. But he was my Earth and Planetary Sciences professor at MIT, and we talked a lot about waves there and about how ocean currents and waves happen. So Huygens was the guy who really put forward the wave theory. Newton was with the majority of the Greeks who said it's a corpuscle or it's a particle, that light must be corpuscles or particles. And remember, Huygens wins the day from not because of his experiment, but because of some of the implications of waves, some of the things people observe with waves, and an experiment we will study in the next unit, which has to do with the dual slit experiment. So waves radiate out from a source, and it's important, this word radiate, and I should probably put it in our definitions. It means we have a point source and it moves out in all directions. Light is a form of radiation. It moves out in all directions. Waves are energy radiating through a media. They move out in all directions, but they don't always appear to, which is part of what we're talking about today. All right, this is going to end my first section. I have to do this in 10-minute bursts, so we will come right back to this in my next section. All right, talk to you soon. Bye.